So this is kind of a review. So remember that we defined the natural log of x as being the area underneath the 1 over t dt curve. So it's this reciprocal relationship, the one value of n where the formula for power rule doesn't work. So we define the natural logarithm as such, as the area underneath the curve from x equals 1, or t equals 1 in this case, to t equals x. And if you go to t equals, or x equals 2.712h, you get an area of 1. The natural log of e is 1. And from this definition, you can also see that if x is greater than 1, then you're going to have a positive area because the upper limit is going to be greater than the lower limit. And so with the function above the x-axis and the upper limit being greater than the lower limit, you should end up with a positive area. So the natural log is greater than 0 for x greater than 0. For x greater than 1. For x equals 1, the natural log is 0. And for x less than 1, you still have an area, but because the upper limit will be less than the lower limit, then you get a negative area associated with this part of the curve. So even though I have a positive area underneath the curve, because I'm integrating from 1 to a lower number, I get a negative result. Okay, so that's how we define the natural logarithm. What else? Because of the way we define the natural log, the derivative of the natural log is just 1 over x, because the integral of 1 over x is the natural log. So we said we define the integral in this case. We define the function by the integral, and then we therefore had the rule for the derivative. The derivative of the natural log is 1 over x. Now, if the argument of the natural log function is something u, what you do is use the chain rule. So you take 1 over u, which is the derivative of the natural log of u, and you multiply by the derivative of the argument with respect to x. So for example, if I want to take the derivative of the function the natural log of 1 plus x squared, you take 1 over the argument. So we take 1 over 1 plus x squared, and we multiply it by the derivative of the argument. So the derivative of the natural log of 1 over x squared is 1 over 1 plus x squared times 2x, or 2x over 1 plus x squared. Okay, so that's just the chain rule. And we ended up with these rules. So we ended up with the derivative rules, but there are corresponding integration rules that say the integral, in this case the indefinite integral. So the indefinite integral of 1 over x dx is the natural log of the absolute value of x plus c. If you make it in terms of u, the integral of 1 over u du is the natural log of u plus c. So this is u substitution. Well, this is u substitution. The book has this version, which is basically u substitution as well. You know, if you can get, but I don't use that because it's confusing. It's better just to say this is just a new formula for using u substitution. And if you don't have just 1 over x, if you have 1 over something times the derivative of that something, then you can make the appropriate u substitution. What's the significance of the absolute value? We already talked about that. And that was because if you look at the function on the negative side over here, you also have an area. And as long as you integrate from a more negative number to a more positive number, then you should have an area. It should be negative because it's underneath the x-axis, whereas when we integrated this on the positive side of the x-axis, we had a positive area. So when we integrate similarly in the domain from 0 to negative infinity, and we integrate from one value of x to another value of x, because it's below the x-axis, we should get a negative area, which we do. Okay. And the reason we get the negative area is because our lower limit is more negative than our upper limit. Okay, so we already looked at that. And let's skip over that one. Let's and we also looked at the integrals for the other trig functions by using the integral of 1 over u du. So remember what we did here was we said we can rewrite the tangent as the sine of x divided by the cosine of x dx, and we let u equal the denominator, and then therefore we take the derivative of that and we get negative the sine of x dx. The derivative of the cosine is negative the sine of x dx, which this part, therefore this part becomes negative du, this part becomes u, and when you integrate that, the integral of 1 over u du is the natural log of u, and you have the negative sign, so you get the natural log of the absolute value of u, which is the cosine of x. And we already did that, so I'm just reminding you what we did. And we did the same thing for cotangent, or we said we could. And then you can also do it for secant and cosecant. We had to multiply this by the sine of x plus the tangent of x divided by the sine of x plus the tangent of x, and did a little manipulations, and we showed that was true. Okay, so we've done all that already. That's section 2. Okay, so that's your homework assignment. I keep forgetting I'm not attached here. I'm attached. So go ahead and write that down. I got my new microphone in the mail. It does work. I just haven't decided what to do about it yet. I think I'm going to keep it. It also doesn't give you that feedback. You know, I was having that problem with the kind of a weird noise with the other microphone. This one doesn't do it, so apparently it's the microphone. So I've got my I put theirs in the bag. Anything exciting happen over Thanksgiving? I didn't do much. I was lazy. I thought Friday. I'm always like, oh yeah, I'm going to do something, and then I never do anything. I'm sure you never had that feeling, right? But it doesn't go away. Thank you for the people that came to listen to our group. So you three, was anybody besides you three guys? No, I think so. Yeah. So Mike came all the way from Buena Vista. Yeah. And her friends. She brought 3 people. So we're actually going to skip section 3, and I'll explain why. So section 3 talks about inverse functions. So you guys have had inverse functions before in pre-calculus. I'm going to give a short summary of inverse functions. We're not going to go into a lot of detail. So what you probably remember about inverse functions so there's no homework out of section 3. So what I remember about inverse functions is that let's say what we can say is f of x and g of x are inverse functions if f of g of x equals x and g of f of x equals x. And you mostly did that for linear functions in pre-calculus because it was in your first chapter. So I'm not going to go through the whole procedure, but you might have some kind of linear function, y equals 3x minus 1, and you want to find what the inverse of that function is. And to do that, what you do is you switch the x and y values. So x becomes y and y becomes x. And then you solve for y. It's not that hard, so let me just show you. So you would get x plus 1 is equal to 3y. Y is equal to x plus 1 over 3. Okay? So these two are inverse functions. If you said f of x equals 3x minus 1 and g of x equals x plus 1 over 3, if I did f of g of x, I would get x, and if I do g of f of x. So when you do, say, f of g of x, the way that works is you take f of x and you plug in g of x for x. So you put in x plus 1 over 3 minus 1. So I'm plugging in this for there. And you can see these cancel out. You get x plus 1 minus 1, which is equal to x. And then g of f of x equals, then what you do to go the other way. So you take, I did this one into that one, and I could do that one into that one. So that would be 3x minus 1. So I put this value for y into where x is here. So I'd get 3x minus 1 plus 1 divided by 3. And that also equals x if you simplify it out. But the key thing here is that for our chapter, there's two sets of inverse functions. One is, we can say e of x, e to the x, and the natural log of x are inverse functions. And you use that a lot in pre-calculus because what you could, if you say f of x equals e to the x and g of x equals the natural log of x, if I do f of g of x, then I'll have e, and then for x I'll substitute in g of x, so I get e to the natural log of x. That's equals x. And if you take g of f of x, that's the natural log of e to the x, and that's also equal to x. So that's the main about inverse functions. And we could use that to solve for x in logarithmic or exponential equations. So in calculus, we introduce e to the x as the inverse function of the natural log of x. There's also two other things about inverse functions that I haven't mentioned. One is that if you plot inverse functions, two functions that are inverses of each other. So if I plot e to the x, which looks something like that, and I plot the natural log of x, which looks something like that, and you draw the diagonal line y equals x, so that's y equals x. The other property of inverse functions is they are symmetric around the line y equals x. So, this function is as far from this axis or this diagonal line as this function is. They're mirror images of each other. So you can always check to see whether you've done something. If I wanted to confirm that these were inverse functions, I could plot them, and I would see that one is on one side of the, well, they would be mirror images across that line y equals x. And what's the other one? There's another thing about inverse functions. Yeah, I can't think of it what it is now. Okay. So the question would be, what is the what are the formulas for the natural log of x? I mean, for the integral of e to the x and the derivative of e to the x. So let's say that f of x, or let's say y, let's not call it f of x, let's say y equals e to the x. So I want to take the derivative of that. So what I'm going to do is I'm going to use logarithmic differentiation. So what that means is I take the natural log of both sides. And the properties of logarithms say that I can convert the right-hand side into x times the natural log of e. I could have also just said, I also could use the inverse properties of the natural log and e to the x, but either way works. The natural log of e is 1. So what I end up here is the natural log of y is equal to x. That's my simplification using the properties of logarithms. And then logarithmic differentiation says that you take the derivative of both sides with respect to x. So once I've simplified it using the properties of logarithms, I take the derivative of both sides. And so the derivative of the natural log of y, because this is y and this is a y variable and this is x variable, we have to use implicit differentiation. So what I get on the left-hand side is 1 over y times y prime. So the derivative of the natural log of x would be 1 over x, but the derivative of the natural log of y is 1 over y times y prime. And the derivative of x with respect to x is 1. Okay, so that's the next step in logarithmic differentiation. And then I solve for y prime. Y prime is equal to y. So multiply both sides by y. And then I go back to my original equation and I plug in what y was equal to. And I get y prime is equal to e to the x. So what that says is the derivative with respect to x of e to the x is equal to e to the x. You can also say that also the integral of e to the x dx equals e to the x plus c. Because if the derivative of e to the x is e to the x, then the integral of e to the x is e to the x. So those are my derivative and integral formulas for e to the x. And so there's a lot of interesting things that come out of the fact that the derivative of the function is the function. That e to the x is the only function that happens for. So we'll see, you see a lot of e to the x in a lot of physical situations, because part of the reason is because the differential equation is this, and the solution to that differential equation is this. But we'll get to that in chapter 6. But for right now, we have two formulas. We can also say, hey, we could do u substitution if everything works out right. So, the integral of e to the u du is equal to e to the u plus c. So we can put u in there. That just means that we can use u substitution. So the rest of this section is just applying these two rules, the derivative rule and the integral rule. So we'll come back to that, but I just remembered there was something else I wanted to talk about that we didn't cover in section 1, so I'm going to do that. Oh, I'm trying to I want to save it. I saved it as a template. I didn't mean to do that. Actually, I'm just going to continue on. I'm not going to open it up because I remember how to do this. So what we're going to do here is we're going to use logarithmic differentiation to prove that the derivative of x to the n is equal to n times x to the n minus 1. So you remember back in chapter 4, or actually in chapter 2, the way that we came up with this relationship was that we tried a couple of values of n, and we used the limit definition for the derivative. You know, the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And we tried a couple of values of n, and we saw this pattern, and it looked like this would be a good rule. And so we said, let's use the rule. But you can prove using logarithmic differentiation that n can be any value. It could be the integer, it can be a decimal, it can be an irrational number, it doesn't matter. And this is probably the easiest way to show that it does work for all situations. So what we would do is we would say y is equal to n x to the n minus 1. So what I want to do is use logarithmic differentiation. So the way we do that is we take the natural log of both sides. So we have the natural log of n, pardon me, and that's not what I wanted to do. Sorry. I just wanted x to the n. I don't know why I did that. I gotta hit myself. So we want to know, what is the derivative of x? We want to prove this is true. So here it is, y is equal to x to the n. So we take the logarithm of both sides. So we get the natural log of y is equal to the natural log of x to the n. Then we use the properties of the logarithms, which in this case says we can bring the exponent out front. So that's our simplification using the properties of logarithms. Then we take the derivative of each side. And n is just a constant, so I can bring that outside of the integral. I mean the derivative. Okay, so now we're going to take the derivative of this and the derivative of that. Well, the derivative of that we just did a second ago is 1 over y times y prime. The derivative of the natural log of x with respect to x is just 1 over x. We don't have to put the y, we don't have to do an x prime or anything. So this is just our normal definition of the derivative of the natural log of x with respect to x. Okay, so that's taking the derivatives using implicit differentiation on the left-hand side. Then what we do is we multiply both sides by y. So we get n times 1 over x times y. But we go back to our original expression here to rewrite the whole right-hand side in terms of x. So for y, we put in x to the n. So we'll have n times 1 over x times y, but y is x to the n. And then if you use the properties of exponents, we can combine these two, and because that's in the denominator, we're going to subtract the exponent. So you get n times x to the n minus 1. So there you go. So that's the rule, and I didn't make any assumptions about n being any special kind of number. It was just a number. So I took the logarithm both sides, used the properties of logarithms to simplify it. Then I took the derivative. Once I took the derivative, I solved for y prime. And then finally I plugged in what my original expression was for y, and then I simplified, and I got the result. So that's You can also do the same thing for the product rule, or I guess you can do it for the product rule. So let's say you have f of x equals, well, we just have two functions, I guess. We have f of x and g of x. And if we said y is equal to f of x divided by g of x, multiplied by. You can also do the quotient rule, but let's do the product rule. So if you take f of x times g of x, so I'm not making any assumptions about what these are, they're just general functions. So if I use logarithmic differentiation, I would take the natural log of both sides, and then I'd use the properties of logarithms. So what I can do is I can break that product up into a sum, like that. So, the natural log of a times b is the natural log of a plus the natural log of b. So that's my simplification. I've changed the product into a sum. Then I would take the derivative of both sides with respect to x. So the left-hand side, I use implicit differentiation. The right-hand side, I just use the chain rule. So what I get is 1 over f of x times f prime of x. So I take 1 over this argument times the derivative of the argument, and the same thing's true here. I'll get 1 over g of x times g prime of x. I solve for y prime, so that's going to be equal to y divided by f of x times f prime of x plus y over g of x times g prime of x. So all I've done is multiplied both sides by y to make this equal 1, and I get y over this and y over that. And then finally, what you would do is you would substitute y back in. Well, y was equal to f of x times g of x. So you get y prime is equal to y, but that's f of x times g of x, all divided by f of x, and then multiplied by f prime of x. That's the first term. So y is f of x times g of x divided by f of x times f prime of x. The second term is f of x times g of x divided by g of x times g prime of x. And you see these cancel out, and you get g of x times f prime of x plus, these cancel out, f of x times g prime of x, which is the product rule. So that's, what we're doing here originally was taking the derivative with respect to x of the product of the two functions. And using logarithmic differentiation, we proved that it's the normal product rule that we derived. We derived this in chapter 2 using the limit definition. So there are a lot of formulas that we can derive using logarithmic differentiation that we had to resort to using the limit definition in chapter 2. So it's kind of interesting. Will you be responsible for doing those? No, this is just more for your, just to give you some examples of using logarithmic differentiation. Okay, so that's my back and pass. Now we'll move forward. Let's just so inverse. Okay. So here's a function, y equals e to the x squared plus 2x. So the formula that I use says that the derivative with respect to x of e to the x is equal to e to the x plus c. Or you could use a u if you wanted to use a u, but let's just use the chain rule. So use the chain rule. Chain rule, f of u equals e to the u. U of x equals x squared plus 2x. So we take the derivative of this. Well, if e to the x, derivative of e to the x is e to the x, then the derivative of e to the u is e to the u. The derivative of the argument or the exponent is 2x plus 2. Chain rule says f prime of x equals f prime of u times u prime of x. So we get f prime of x using the chain rule as e to the u times 2x plus 2. And then we substitute u back in, so we get e to the x squared plus 2x times 2x plus 2, or put the linear part in front. So that's the derivative. And again, you can, once you get good at this, you don't need to write this if you know what you're doing. You just say, the derivative of e to the x squared plus 2x is e to the 2x squared plus 2x times the derivative of the exponent, which is 2x plus 2, and you could go straight to that result. You just look at your original function, take the derivative of the exponent, and multiply by the original function that you had. So let's just make one up and just try to do it in our head instead of using this extended version, the larger version of the chain rule. So if I said g of x equals e to the x cubed plus 3x, what do you think? Write down what you think the derivative should be. So over here what we did is we just took the derivative of the exponent and then multiplied it by the original function. So that same thing's true here. Take the derivative of the exponent, multiply by the original function. Okay, I already did that. Just did that. And actually, we didn't do that one. So again, think about this. Y prime, take the derivative of the exponent, multiply by the original function. Now the next one is just to show that if you have a product rule, you have to use the product rule. So what you would do is, remember, the product rule says you take the first term, multiply by the derivative of the second term, and then add the second term times the derivative of the first term. And when you take the derivative of e to the minus x, again, instead of writing out the whole chain rule, it's so easy to do. What is the derivative of negative x? Negative 1, right? So the derivative of e to the minus x is just negative e to the minus x. So you never change the argument through differentiation or integration. So we do this so often, you might as well try to remember it. So the derivative of e to the minus x is just equal to negative e to the minus x. Because you take the derivative of the exponent, which is negative 1, and you multiply it by the original function. So when you take away the 1, which is redundant, you get that. So you can use that here. So if I do y prime, it's going to be equal to the first function times the derivative of the second function plus the derivative of the first function times the second function. So this is f of x times g prime of x plus f prime of x times g of x. And you wouldn't leave it that way. You'd clean it up. You'd take the negative sign out front. And you could drop your little multiplying thing there. So that would be the derivative. And remember, just so you don't get points taken off next time, notice how I put negative e to the minus x in parentheses. And that was so, if I didn't have the parentheses, I might think I'm supposed to be subtracting this, but I'm not. I'm multiplying by negative e to the minus x. Now once that negative sign came out front, then it wasn't, you didn't need it anymore because it's obvious. I put this little dot here because I'm trying to show that this is the product of this times that, but once I have done that, I can take this out and just put the numbers right next to each other to show that they're being multiplied together. Now this one, you would have to rewrite this as 2 times e to the x plus e to the minus x to the minus 1 power. So you'd have to use the chain rule. Once you've rewritten this and move this to the numerator, you would say f of u equals 2u to the minus 1 power, and u of x equals e to the x plus e to the minus x. So if you take the derivative of this, you'd get 2 times negative 1 times u to the minus 2 power, and the derivative of this would be, you just have two terms, two separate terms. So you take the derivative of e to the x, which is e to the x, and you take the derivative of e to the minus x, which would be negative e to the minus x. Just the same reason we ended up with a negative sign over here. So f prime of u is negative 2 divided by u squared. So I've taken this to the denominator. There's nothing you can do with the u prime of x. So you'd say f prime of x equals f prime of u. In this case, I'm writing it out because it's not simple. So you can't always just do it in your head. You might be able to, but so you have negative 2 over u squared times e to the x minus e to the minus x. And then you would plug back in u, so you get negative 2 over u squared. U is e to the x plus e to the minus x. That whole thing squared times e to the x minus e to the minus x. Again, I'm putting in parentheses, so I know that I'm multiplying this by the whole quantity. And then you probably would just combine these two. So you'd end up with negative 2e to the x, negative 2e to the x plus, because you have a negative times a negative, 2e to the minus x, all divided by e to the x plus e to the minus x squared. Okay, so I'm assigning that as well. I did give you a handout. I thought there was two sides to the paper, which are not. Oh well. Those will all be due next Monday. You know, it's kind of good that we have this chapter 5 anyway, because we learn new material, but we have to go back and review material that we've probably forgotten already, which is how to take derivatives. And you'll have to do that on the exam anyway, so in terms of I think we got an exam schedule. I think our exam's the first one, like first day, first. Yeah. Okay. So what we'll do tomorrow is, I'm not finished yet. Don't get excited there. What we'll do tomorrow is we'll go through some more examples. We'll let you work them out. So we'll have a handout to work on. So what we've seen is that the derivative of e to the x is e to the x. And you just use the chain rule as you would normally use the chain rule. If it's part of a product, then you have to just treat it as part of the product. So there's nothing especially insightful after you've determined what the derivatives are and what the integrals are. Same with integration. What we have to do is we have to put if it's not just e to the x, if it's e to some power of other than x, we have to have the du, the appropriate du, multiplied by e to the u to be able to integrate. So that's what we'll see here. That's not the one I wanted to do. Where am I? I'm just trying to find a. Oh, I see what's going on. Okay. There's another section here that I've got to open up here. There we go. Integration. Okay, so let's just do a few problems before the end of the period. So, because the argument is not just x by itself, the only way this thing is going to work out is if the derivative of this, the derivative of this is what's left over. If it doesn't match it up, then we can't do the integration. So it's going to have to work, or we're stuck. We don't get problems that say, can we do this or not? We just say, can you do this, because you can do it. You know, it's not. We're not going to give you something you can't do. So what you would do is you'd use the u substitution, just like we've normally done. So u substitution says you typically take the argument, which in this case is the exponent, of the function. So we're going to let u equal the square root of x, which is equal to x to the 1/2 power. And then we take the derivative of that. Well, the derivative is going to be 1/2 x to the minus 1/2 power. So we multiply by the exponent, reduce the exponent by 1, and we multiply by dx. And if we rewrite that, you'll get 1 over 2 square root of x dx. So we take a look at that and say, is that what we have here? Well, we don't have it exactly. We have dx over the square root of x. So we'll solve for dx divided by the square root of x. that's going to be equal to 2 times du. So the substitutions we're going to make is we're going to for the square root of x, we're going to put in u, and for dx over the square root of x, we're going to put in 2 du. And if you make those two substitutions, we have the original integral becomes e to the u times 2 du. We factor out the 2, and we have the integral of e to the u du, which is exactly what we need. We need that. So once you get to that point, you just use the formula. Formula says the integral of e to the u du is equal to e to the u plus c. And then finally we go back and substitute u back in, so we get 2e to the square root of x plus c. So that's the answer. That's the indefinite integral of the original expression. Now this one may not look like it's going to work, but it has to work because we wouldn't give you one that didn't work. So I choose u to be the, you might think, well, I could choose u to be e to the x, but that really doesn't do any good because it's still, that's not, if I let u equal x, that's not going to help me any. It's the same equation just with u instead of x. So I can either choose the numerator to be u or I can choose the denominator to be u. Well, if I choose the numerator to be u, the derivative is not going to be 1 over that thing. So what we're going to do is we're going to choose the denominator to be u. So if I let the denominator equal u, and then I take the derivative of the denominator. So the derivative of e to the x is e to the x. The derivative of e to the minus x is minus e to the minus x. And I multiply that by dx. You'll see that I have the numerator now. E to the x minus e to the minus x times dx. So I have the direct substitution I can make. So again, I'm going to substitute for these two, I'm going to substitute du. Actually, wrong one, it's the numerator. Sorry. So these two, I can substitute du. And the denominator I can substitute for u. So what I get is 1 over u times du. And so in this case, it's not the exponent that is the substitution that I'm making. I'm making the substitution for the entire denominator. So it doesn't end up being the integral of e to the u. It turns out it's the integral of 1 over u du. And the integral of that, you go to your formula sheet, and it's the natural log of the absolute value of u plus c. And then I go back and plug in what u is, so I get the natural log of the absolute value of e to the x plus e to the minus x plus c. So that's the answer. Again, the whole idea of u substitution is that you have to convert your original integral into an integral that is in the table of integrals that are in our book. So even though you see e to the x and you think, oh, I'm going to integrate e to the x, that's not necessarily true. Okay, that's what this problem is supposed to be demonstrating. But I'm going to give you one to work on here. Then we'll end with this. So what's the integral of okay. So what's the integral of 4x cubed plus 2 times e to the x to the fourth plus 2x dx? In this case, the argument is something other than just e to the x or e to the minus x. So you're going to choose this to be u. Okay, so we let u equal x to the fourth plus 2x. Take the derivative of that, you'll get 4x cubed plus 2. That's how I chose that in the problem. Multiplied by dx. Notice I put it in parentheses. You don't want to leave the parentheses off because that looks like 4x cubed plus 2, just 2 times dx. So you need the parentheses. So making those two substitutions, this is e to the u. This and that is du. The integral of e to the u du is e to the u plus c, and then we plug u back in. Am I going to assign that today or tomorrow? Well, I'll assign it. I'll give it to you today, but it's not due till next Tuesday. Actually, considering the test is next Thursday, we may, you might want to do it by Monday anyway, so you'll leave time because you're going to have some more. We're going to talk about inverse trig functions here sometime. Okay, so we'll practice some more tomorrow.